grabar y emitir y demás.
Han aclarado lo que nos van a dar, pero básicamente ellos cobran 4.000 euros de gestión.
Voy a grabar ahora, Gerardo.
Ok, igual tengo que darle algo.
No. Grabar y emitir y demás. Okay, good morning, everybody. There is a micro still open. Voy a grabar ahora, Gerardo. Oh.
Ok, igual tengo que darle algo.
No. Wait. Grabar. Okay, thank you very much for being here and welcome for this new seminar. Today we will have the very nice talk by Gerardo García Moreno from the Instituto de Astrofísica de Andalucía, and he will talk about, is it possible to simulate time machines in a laboratory? Gerardo García Moreno studied physics at the University of Complutense in Madrid between 2015 and 2019, and then the master in theoretical physics at the University Autónoma de Madrid. During this time, he got over of a number of scholarships and summer scholarships also in the Institute of Fundamental Physics, then in the Institute of Theoretical Physics, both of them at CSIC in Madrid. And then in the Institute of Photonic Science in Barcelona. Then he started the PhD here at the Instituto de Astrofísica de Andalucía in October 2020, under the direction of Dr. Carlos Barceló, Dr. Carlos Luis Garay from the Complutense, and Raúl Carvalho, currently at the University of Odense in Netherlands. Then he has the scholarship for doing the PhD. So thank you very much, Gerardo, for giving this talk, and I'm sure it will be very interesting and I will be here. So the floor is yours.
Thank you, René, for the nice introduction. So, as you've said, today I'm going to be talking about whether it's possible to simulate time machines in a laboratory. So, first of all, let me give you a brief outline of my talk. Since today is the first time that I publicly speak in the IAA, I'm going to give a short introduction in which I will talk about the things that are my research lines and my scientific activity to give you a taste of the things I work on. And then I'll jump on to the last three items that I showed there, which will be the main part, my main talk today. First of all, I would like to talk about general relativity and what is the status of time machines in general relativity. I will discuss whether these things are possible or not, what do we think, what the community thinks about it. Then I will jump to discuss analog gravity, which is a research program in which we try to reproduce gravitational phenomena in laboratories, which is this second item. I will briefly explain why we are interested on it and the things that we can learn about physics and gravitational phenomena from it. And then finally, I will discuss, after these two introduction of these topics, I will discuss our last paper that I did with Carlos and other collaborators on whether it's possible to simulate these time machines there. So first of all, let me introduce myself. And I'm my research line is high energy physics. I'm a high energy physicist, and I'm interested in understanding high energy physics. Because of special relativity, this means also very short length scales. And actually, I'm interested in putting together gravity and quantum field theory, which is essentially what the theory that describes particle physics, the standard model of particle physics. And in doing that, we don't have reached yet the energy scales at which quantum gravity is expected to be relevant. which are essentially 10 to the 19 giga electron volts, or in length scales 10 to the minus 33 centimeters. But in any case, we think it's useful to think about the kind of imprints on low energies that this kind of quantum gravity theories that are relevant at high energies may have at low energies. In a sense, I'm not interested in any kind of particular approach toward quantum gravity. I don't do a string theory, or I don't do quantum gravity, but I care about what are the physical consequences of these things. How can we measure things that come from those theories? Also, one thing that is characteristic of what we do is that we pay a lot of attention to condensed matter physics. This means systems that you can engineer in the laboratory, and draw up conclusions and learn things that we can infer from the behavior of those systems with respect to quantum gravity. And actually, it will be what I will be talking today. But before that, let me tell you that essentially there are two situations in which we expect gravitational phenomena to be intense enough or strong enough for quantum gravity to be relevant. One of them is cosmology, the very early universe. I won't discuss much about that today, but the other one is black hole situations. Actually, I don't study much black holes, but what we call black hole mimickers. These are things that look like black holes in the sense that they reproduce the electromagnetic and gravitational wave observations that we have of black holes, but instead they don't have the pathological behavior that general relativistic black holes have. For instance, they are not singular and they don't have event horizons. So within this context, you see here a bunch of things that I'm working on now. First of all, we are revisiting the famous no-hair theorems of general relativity. This means in general relativity, black holes are supposed to be characterized just by how massive they are and how fast they rotate. But when you depart from general relativity, you study modifications that can come for instance, from quantum gravity, you soon break these no-hair theorems. So we are understanding how you can break them and what things survive of these no-hair theorems. Or we are studying bouncing models in which instead of forming a singularity after a star collapses, you stabilize an object, maybe after a little bit of oscillations and all that. But this is the way in which you would form this object. This means it could not collapse until you have a singularity. And also I'm interested in how these objects could have a differential accretion behavior from black holes, or how you can launch these ultra-relativistic jets that these black holes that we observe in AGNs, because it seems to be different the mechanism that acts on this kind of black hole mimickers than the one that acts in ordinary black holes. Also, another topic which is more related, actually is the topic of my talk today, is what happens when you push the causal conditions of general relativity, the structure of causality that you have in general relativity, to its limits. This means essentially I'm at very short scales. We think spacetimes are Lorentz invariant, but from many quantum gravity approaches, we expect Lorentz invariance to be violated. And just here I've put some items which are the tools that I use every day, just in case sometime you hear about them. These are the things that I fight against every day: effective field theories, quantum field theories, and all that, which is the way in which we describe Lorentz invariance violations. Actually, today I will focus especially on this superluminality. Once you break Lorentz invariance, you can send superluminal signals. And I will focus on the problems that appear when you have superluminal signals, because it's very easy to engineer a time machine once you are allowed to send superluminal signals. This is something that I'll discuss a little bit later. So just as a remark, the interest in analyzing this issue of the building time machines is not just because it's funny per se, but in the meantime, when you try to build these time machines, you're pushing your theory to its limits, and you might be proving a more microscopic and fundamental structure that appears in nature when you try to do this. Even if you don't manage to build it, you will be testing nature to scales that you wouldn't test in another way. So in this talk, I will focus on condensed matter physics, which can be done, realized in laboratories, and the issues of that appear when I have superluminality. So this finishes sort of my introduction for you to know what I work on. And now I'll jump to the main part of the talk, and we will first discuss general relativity. So first of all, a question: who's here familiarized with general relativity? Please, hands up. Come on, Victor. Okay, hard audience. So let me just briefly review what's general relativity. I will begin with the basics. What's the kinematics of general relativity? Space-time in general relativity is described as a curved manifold, which is a very fancy mathematical word, but you can think of space-time as a curved surface. This means take a piece of paper and fold it. That's where space-time is. Light rays in that folded space-time follow the straightest, you can exchange this word straightest by shortest, possible paths in this surface. This is the basic kinematics of general relativity. This we encoded mathematically in a metric, which is the subject g mu nu that I'm representing there, which is a tensor and all that things. But equivalently, you can think that this g mu nu is encoding the light cone's structure of this surface at each point. This means if you zoom one of these squares enough at sufficiently short scales, every space-time looks like this. Looks like time flowing in one direction, space in the other, looks approximately flat if you zoom enough. And you have at each point P that I'm writing here, a light cone. Actually, you have two. The future light cone, which is depicted in green here, and the red light cone, that is the past light cone that is depicted in red there. The locality principle, which is underlying general relativity, tells us that we can send just information within this future light cone, just between the borders of this green cone. Actually, the closest you send this information to the boundary of the cone, the fastest information is moving to the future. So this is a crucial point. And in my talk, I will be using this kind of code color for the light cones all the way. So for you to remember, I've chosen to put these two pictures in which Kermit, Rana Huevo for the Spanish speakers, will represent the things that we can do. I mean, we can go in that direction. Kermit is going to be trying to move to the future always. And we have also this red panda from the recent film Red. That has anyone here seen the film Red? Okay, I expected those that had kids to have seen it. So I'm not sure if the film is about this, but I'm pretty sure it is. It's about a red panda that gets very angry when someone tries to go back in time, right? Thank you. So that's the argument of the film. So whenever we do fancy things in my talk today, we do things like trying to go backwards in time, this red panda will appear, telling us that we cannot do it. So now that I've discussed the kinematics of general relativity, it's time to move and discuss the dynamics. Essentially, the dynamics of general relativity is encoded in Einstein equation, which are these things that I've written here. We have the left-hand side, which is the Einstein tensor, encoding the space-time curvature, telling us how much curved is a space-time at a given point, and the right side, which tells us the energy density at a given point. This means the energy, essentially, that we have. So in that sense, Einstein equations simply relate how much energy is there at some point with how much curve is the space-time at that point. From this perspective, the curvature can be equivalently thought, this is a very nice pictorial way of thinking about it, as a tilting of the light cones. Whenever we don't have a gravitational field, as I depict here in the left lower picture, the light cones flow normally to the future. Whenever we have a gravitational field, this is what that D in the right hand side represents, the light cones tilt. And actually, the closest you are to the object emitting the gravitational field, the more tilted the cones are. As I told you before, this the closest you move to the border of the light cone, the fastest you move to the future. So if you are closer to the border of the light cone when you are closest to the object, time flows for you much slower than for someone that is very far from the surface of the object. This is exactly what happens in the film Interstellar. In Gargantua, you have your light cones when they go down very, very tilted. So this is essentially what happens in Gargantua, and also these things are required to be used by your GPS for you to not get lost. So now this is a little bit a departure from my talk, but I thought it was interesting to illustrate with this picture of the light cones what an event horizon is. This is a star, a spherical star. I'm just drawing here a circle because obviously I cannot draw more dimensions in a paper. So this star is collapsing until it forms a singularity at that point. And this gray shaded region is essentially what we call the black hole. It's the black hole region because the light cones tilt so much that whenever you are parallel to this event horizon, the locality principle tells you that you need to flow into the gray shaded region, and for you it's not possible to escape to the white region. So in a sense, a black hole is essentially something with a gravitational field so strong that the light cones have tilted so much that you cannot escape from that place. So within this context, one may try bueno, ya da igual. Sorry. So within this context, we can think of a CTC. This stands for Closed-Timelike-Curve. This means a curve such that the light cones are always flowing to the future, and an observer can stay at a given point, go through this loop, and come back to the same point without violating this locality principle. This thing, you can conceive a geometry. You can write down examples in which this occurs. And essentially, this is what would represent time travel in a sense, someone coming back to the same point, to the same space-time point. Of course, this is not problematic from the point of view of locality because you're always flowing within the light cone, but it's weird. I agree that it's a weird situation. However, we have solutions like this in general relativity. This means some things that solve, some geometries that solve Einstein equations and display this behavior. For instance, the most famous one was probably by a mathematician called Godel, which is one of the greatest mathematicians in the 20th century. And they display this behavior. However, it's not so interesting for us because it's not something that we experience in our ordinary lives. We are not plagued by time travelers. So we are more interested in having a space-time which has a normal causal behavior, and at some point we manage to generate just one of these CTCs, and then time flows again. I'll put a picture in a moment. So this situation occurs in general relativity, but it's not so interesting for us. Let me just now discuss something that I mentioned in the introduction, and it's how superluminality and time travel are very related. Special relativity is okay for people here. Okay, so imagine that I have two reference frames, this one with the axis in blue, Tx, that I represent there, and the other one with the axis in red that I represent there. Let me call this one S and the other one S prime. And as you see, because of the twisting of the axis, this one is boosted with respect to the blue one. This means there is a Lorentz transformation relating them. And imagine that we are able, also these dotted lines represent the light cones at each point, obviously. Imagine that I'm able to send superluminal signals. This means that instead of flowing within the interior region of the light cone, I can go send signals outside it, okay? So this in principle is something that I'm allowed to do. So send a signal from this point to P prime, which is the origin of the other frame of reference. Now, an observer that is lying here is, for him or her, it's also possible to send superluminal signals. This means that he can send signals within this region of the light cone and this region of the light cone. And the issue is that the unique constraint that he needs to fulfill is that it goes to positive values of t prime, if this is t prime equals 0. And this is fulfilled by this second trajectory that I draw here, which goes to the past of the point t. So in this sense, it's possible for these observers to send, like to engineer time travel, essentially, because this one is sending information to this one is sending back to his past, and in this way, you've managed to send information to your past. So this happened with superluminality. Just as an aside, it becomes relevant later. As I was saying before, the kind of situation in which we are more interested is the one in which we have a normal time flow, and at some given bounded region of our spacetime, we are sort of engineer this kind of ear that we glue to the spacetime, and this ear is a time machine. This means that it has trajectories that go backwards to the same point and then go to the future. In our knowledge of general relativity and the standard model of particle physics, it's possible to do this. It requires negative energies, which are something that is tightly constrained. We cannot manipulate at will these negative energies, but theoretically it's possible to conceive a situation, a future, a very advanced civilization or something like that, that is able to do it. So for that purpose, I'm gonna tell you a story about someone that tried to do this, which is Kermit, the frog, that wanted to time travel, that I'm putting it here for you to see it. So this is the story of Kermit. Kermit was a very happy baby frog that grew up and became a high school student. So at some point in his life, he decided that he wanted to engineer a time machine. He wanted to be a time traveler. So he decided to study physics. He struggled with math, but he passed his exams and he became a graduated Kermit the Frog. So, oh boy, how fast they grow. So this Kermit the Frog wants to engineer a machine. So essentially, he is able, now that he knows a lot of physics and he manipulates at will negative energies and all that, he's able to engineer this time machine. And now he wants to use it. So he travels through the time machine. But now we have a problem. Imagine that this Kermit becomes evil in the time travel, comes back to this point and wants to kill the older Kermit. So we have a problem. It's like the kind of problem, this kind of grandfather paradox, in which you kill your grandfather by using a time machine and you were never born. So imagine now that we have a third Kermit, many Kermits, and essentially he becomes completely mad after all that. So someone is getting angry at this point in my talk because we are doing things that should be illegal. For instance, if we time travel back and Kermit kills his his younger version, how can he travel back in time? This is why the red panda is angry. Essentially, this suggests that this time travel is very pathological and we have to carefully consider it. And essentially, there is a principle of self-consistent histories. This means that you cannot have this kind of setups in which you travel back in time and kill your younger version. Well, since I'm using the Muppets, I want to be family friendly, and that's why I shouted that. And I will describe the example with a billiard ball. Imagine that there is a billiard ball here that goes in this direction, goes through the loop, and finds the previous billiard ball here. But it hits it and deviates from the trajectory. This is another kind of paradox that may appear in this situation. So one has to avoid that. But let's assume that we have avoided it. Furthermore, there is a second problem. The time machine is engineered with negative energy. Every time that our Kermit travels through the time machine, since it's positive energy, you can check it if you want, it will generate an instability. It will try to destabilize this time machine. Also, every time that it goes through the loop, it will interact gravitationally back with the Kermit that already was the younger version of Kermit. And in that way, they will generate gravitational waves. So these gravitational waves will run through the loop. Each time it runs through the loop, it adds to the existing gravitational wave, it'll travel again, and in that way it gets amplified. So this seems to be very unstable. So it seems that our Kermit, poor Kermit, cannot time travel at this point, but he still wants to make a time machine. However, even if you don't travel through the time machine, if you don't use it, there is an instability due to quantum effects. The quantum vacuum, you can never turn it off. And a good way of thinking of the quantum vacuum is essentially as particles and antiparticles that are created and destroyed all the time. You should think about vacuum in that way. And this is something that is allowed by Heisenberg uncertainty principle. You can violate energy conservation, but just on very short time scales as permitted by this bound. And when you do it, it's possible that these particles propagate through the time machine again, very short time scales, but propagate there and destabilize the machine. All these observations on how hard is to engineer a time machine led Hawking to conjecture his famous chronology protection conjecture, in which he usually says that time machines should be forbidden by the laws of physics. There is still a gap in all this, and it's that the considerations that I've been doing apply until you reach this Planck scale at which quantum gravity effects become active. So in a sense, at that scale, we don't have any idea of what space-time looks like, and things can just be very different. So at least for macroscopic scales, those that our Kermit needs to time travel, we cannot engineer this time machine. And essentially, we enter the regime of quantum gravity in which we cannot say much about this. So we have that our red panda is happy because we are not doing chronologically forbidden things. And our poor Kermit is very sad because he hasn't been able to time travel. And also he had a friend that wanted to invest in a time tourism agency, but it doesn't seem to be a very profitable business. So poor Kermit. Okay, so, oops, that's in Spanish, I don't know why. Okay, so at this point, I'm going to move on to the next part of my talk, in which I will describe analog gravity. And essentially, to do it, I will use this analogy. Imagine this river is a fluid, essentially, and these fishes attempt to represent sound waves propagating on top of this fluid. Imagine there is a point, this point of no return, such that the fishes move with a speed of sound much smaller than the velocity of the fluid. This means that all these fishes that are from this point on to the waterfall would essentially be dragged by the fluid. So they cannot escape. But this is precisely the same thing that happens when you have a black hole. But instead of a black hole, it would be a dumb hole. This means this hole cannot speak, in a sense. The analogy is as follows. These sound waves are essentially like light propagating on a black hole. This fluid is essentially playing the role of the substratum, the means where these sound waves propagate or this light propagates. This means it's the effective spacetime that we have. And this black hole is essentially replaced by this kind of hole that cannot speak. To pretend that I'm a theoretical physicist, I will now put some equations. This one is wrong, actually. I leave you as an exercise to notice where it's wrong. So this is the equation that describes sound propagation. So this is in flat spacetime. This equation is from your undergrad studies, so I won't go into details. But let me move on to what happens when you have sound in a curved spacetime. I've written this equation here. For those of you that understand it, great. For those of you that don't understand it, I just want you to notice that here appears this g, this square root of minus g is essentially the determinant of this matrix, this G mu nu matrix. And this G mu nu matrix essentially encodes the, instead of the light cones, since we are now describing sound, the sound counts. This means at each point of spacetime, it tells you on what direction can sound propagate. It is related to the properties of the fluid. For instance, this rho represents the density, this c, the local speed of sound, and this v, the velocity of the fluid. So essentially, this is the way in which we can describe sound propagating on curved spacetime. And this second equation is the way in which it relates to the substratum that we have, to the kind of fluid on top of which it is propagating. So all of this of analog gravity for what, you may ask? Let me just discuss an example of the success of this analog gravity program. And for that purpose, I'm going to tell you very fast about Hawking radiation. As I told you just a couple of minutes ago, it's possible in vacuum that particles create and destroy continuously, as allowed by the Heisenberg uncertainty principle. Imagine that this occurs very close to the horizon, to the event horizon of a black hole. One of the particles may fall and the antiparticle can escape to infinity. So someone that is sitting very far, like Kermit from the black hole, will perceive a flow of particles. Actually, if you can perform the detailed computation, it's a thermal spectrum with a temperature which goes, roughly speaking, with the inverse of the mass of the black hole. Here, I input in h bar equal 1, c equal 1, ev pi equal 1 also. So the issue is that when you plug real numbers here, you plug, for instance, a solar mass black hole, this temperature is ridiculously small. It's orders and orders of magnitude much smaller than the CMB, than the microwave background. So there is no hope to measure this thing on astrophysical black holes. But in analog gravity, we have the same ingredients that we need to be able to have Hawking radiation. This means it's possible to simulate geometries that have a behavior like that of a black hole. And essentially, we can measure, and we can try to measure this on a setup like a laboratory system in which we can control all the parameters of the theory. As many of you have said many times, astrophysics is not experimental, it's observational. This means that you cannot reproduce the conditions that you want a lot of times to perform an experiment. So this is a benefit for analyzing this Hawking radiation. Essentially, this was a proposal that was done in the 80s, but then they realized that the standard fluids are very dirty. This means there is a lot of noise, so you cannot measure Hawking radiation there. But then the 90s came, people discovered Bose-Einstein condensation, and someone very smart decided that it's a good idea to use this Bose-Einstein condensation, these quantum fluids, which are much more clean, since you lower the temperature until microkelvin, nanokelvin scales. They are much more clean. There is not a lot of noise there, and you can try to use them for this analogy. You do it, and there was a proposal in the 2000, and some years later, well, these are Bose-Einstein, the standard picture of a Bose-Einstein condensate, and some years later, Steinhauer which is a researcher, an experimentalist, was able to measure this Hawking radiation in 2016. So this is one of the successes of analog gravity, something that we cannot study in astrophysical scales because we are limited by the kind of observations that we can make and the scales that we play with, can be reproduced in a laboratory, and you can get a lot of information from there. So given this, I hope this motivates why I think it's interesting to study analog gravity. And now I come to the work that we've been doing recently, this paper that was submitted to the archive, which is the electronic preprint version in January of this year. So this was a work that was done with Carlos, which is sitting there, and Joaquin and Jill, which are collaborators. Actually, Jill did his PhD thesis here like 15 years ago, maybe. Okay, so 13 years ago. And we've done this work. Essentially, we tried, since in this kind of analog gravity setups, superluminal dispersion relations are something that usually appears, we thought, okay, so we have superluminality. This is enough to build a time machine. Can we build a time machine? So this is the idea of this work. Actually, we thought we couldn't probably do it, but as I said before, it's interesting to check, to push your theory to the limit. So let me take a step 0 and tell you something about closed-timelike curves that will be relevant later. A closed-timelike curve is one such that your time coordinate can be used as periodic. This means you have this point, you go through the loop, and when you come back to this point, obviously you need to identify this coordinate to be a good coordinate, like an angle. When you rotate 2 pi through a circle, you need to identify back this phi. So essentially, a closed time-like curve, a space-time containing one, is such that you have a time coordinate which is periodic. This is something that will be relevant later. Second, let me make a very stupid observation, which is that in 1 + 1 space-time dimensions, this means one time and one space, I no longer have a kind of light cone in the sense that I just have 2 legs representing the direction in which information can flow. Whether I call these 2 directions, the vertical directions time and the horizontal ones space, is a convention. I could essentially do the same with replacing time and space. This is a very stupid observation, and it's relevant for what I'm going to say now. Imagine that I tell an experimentalist that is a friend of mine to put a fluid on a circle that evolves with time, the fluid propagating on that circle, on a ring. So essentially, from the point of view of a space-time, this is a cylinder because it's a circle plus time. What the experimentalist would do is say, okay, I have a configuration of the fluid on a ring, this pink ring that I have at a given time. My time flow is flowing upwards. So essentially, what I will do is make a perturbation here and analyze how it evolves to the future. The issue is that if he's very, I don't know, if he doesn't feel right that day with working with a ring, that experiment can be equivalently explained as follows. Imagine that he puts the fluid on a line and lets it evolve it, and evolve it in a way such that it is periodic. This means in time. It's a periodic signal, because essentially he just had decided to call the outer part of the light cone time instead of following this convention here. This means it's as if the light cones were completely tilted. So this very stupid observation is simply to tell you that these are closed time-like curves, but they are very stupid and trivial closed time-like curves, and are equivalent to this kind of eternal time-like curves that we have that I described before. For instance, these ones that pass. Okay, I have to go a lot back. This one that passes through every point. So essentially, this kind of closed time-like curves can be simulated in a laboratory, but they are very, I don't know how to say it, stupid, again, in that sense that they are simply a matter of an experimentalist doing fancy things. Now, let me go to the most interesting case for us and for Kermit, which is engineering a chronological horizon. So what's a chronological horizon? As I said before, a chronological horizon is somewhere where you have, it's the boundary of the region that causally behaves well. This means you have an ordinary space-time. At some point, you engineer a time machine, and that point at which you engineer the time machine is a chronological horizon. This means, from the perspective of coordinates and how we describe this, there is this chronological horizon corresponds to the place at which an angular coordinate, which is phi, for instance, an angle, becomes a time coordinate. In the same way that what happens at the black hole is that time and space exchange their nature, here happens also something very similar. This phi coordinate, this space coordinate exchanges its role and becomes time. So essentially in matrix form, this is represented by, in the ordinary situation, we have that the metric has a negative sign for the t coordinate of this GTT component, and G phi phi is positive. When you go to the chronological horizon, this becomes 0. And actually, when you go beyond it and you go to the region in which you have time-like curves, this becomes negative again, meaning that an observer that is moving along those directions is not violating locality. So this is a chronological horizon. Now it comes to the point to see what happens in an analog gravity setup in which you essentially want to identify these components of the inverse metric, which is the equation I wrote before, the sound cones, are identified with physical parameters or system. For instance, the velocity of the fluid, the sound speed, the density, all these things. You essentially can do the math, and since I don't want to annoy you a lot, you end up finding that velocities, for instance, if you are using an analog system, which is a fluid, become infinite. The velocities, the speeds of sound. If you are using an optical analog, which means the electric medium, you will essentially find divergent permittivities and divergent susceptibilities and all that. So this essentially tells us that if someone wants to engineer a time machine in a laboratory, will not be able, because he will have to have infinite fluid velocities. For instance, an example is one geometry that we studied, which was a version of Godel geometry that we sort of modified in order to have just a chronological horizon and closed time-like curves from a point on. This means not eternal closed time-like curves. And whenever you try to do this, you find that the velocities of the fluid and the sound speeds get divergent. So unfortunately, the answer is no. We cannot engineer time machines in a lab. So let me just conclude the messages that I want you to take home. First of all, whenever you hear black hole mimicker, compact object, quantum field theory, Lorentz invariance violations, it's me, talk to me. So the second one is, in general relativity, closed time-like curves seem not to be a possibility, macroscopic ones at least. So time tourism is not a good business. The last ones are strictly related to the work that I've presented. Essentially, the first one is that we can simulate these eternal closed time-like curves, but they are trivial. They are actually harmless. We don't care much about them, but we can simulate it just in case someone is interested on them. And the very interesting case for us, which is simulating a chronological horizon, which is building a time machine, something that we cannot do. So unfortunately, the answer is that we cannot build it. And finally, I just want to emphasize that this is not just a sci-fi thing, which it is also, but the aim of studying these things is not just that you might one day be able to time travel, but the issue is that when you prove the scales at which you need to prove physics to make a time machine, you are actually unraveling the structure of your space-time. What happens in the fluid, for instance, is when you go up in the velocity, you will end up noticing that your fluid is no longer a fluid. So imagine that we are able to try to build a time, it's no longer a fluid, you resolve the atomic and molecular structure of the fluid. If we do the same with ordinary time machines, we may end up finding what's the nature of a space-time itself. So this is one of the things that we need to further investigate. And this is all. Thanks for your attention. Kermit acknowledges you for coming.
Okay, thank you, Gerardo, for this nice talk and for all your efforts to make accessible to everyone these complicated concepts by using analogies, Kermits, and pandas. That's really funny. So the session is open for questions. For the people in Zoom, please raise your hands virtually, and for the people here, raise your hands physically. So don't be shy. Okay, we have one question here in the room. So.
I speak to the microphone. Yeah. Okay. Thank you for the talk. I hope I will understand something. Let's see. My question is related to the loop, where you see that time machine building in space-time. Can you show the picture? That one. Yeah. I was wondering, the space-time through the loop is the same one as in the previous part before making the time machine, or is a complete different space-time due to you said we require negative energy. So applying Einstein equation, the metric is going to change, right?
Okay, thanks for the question, Borja. Actually, the issue with space-time is that you need to see us as a holistic thing, as a whole. This means that the space-time is the whole thing, with the year and everything. The issue is that typically what you do is not think of the space-time as a whole, but just having one slice. This means you cut through a constant time surface and then evolve that. That's what you typically do. So in a sense, the space-time as a whole is the evolution of this surface that you evolve. And yes, the issue is that you need negative energies at some point to engineer this time machine, but the space-time is something as a whole. I don't know if that answers your question.
So it would be a perturbation in the extraction of the metric. So how do you represent that part? I was trying to wonder.
Representing?
Yeah, how can you connect, let's say, physics in that part of the loop with the other thing? Because you're not having the loop, for instance, in the left part. Yeah. But it happens too, I mean, at the same place, or just where the, I don't know how to call it, where you have locally negative energy. Is that the thing that I don't understand? I mean, this is a local part in the space-time where you have negative energy, or as a whole? Yes.
Yeah, sure. Okay, now I understand your point. Here in this region in which you glue the ear, actually in the region in which you glue it, that's where you have negative energies. In this part, you don't need to have negative energies. So I don't know if that, okay, Einstein equations here have a T mu that has negative energies, and here you can have whatever you want to have. But that's, I don't know if that answers your question. Okay, sorry, I didn't understand.
Any other question, either in Zoom or in the room here? Okay, don't be shy. Later, you will not be able to travel back in time to ask questions, so do it now. Okay, no one in Zoom or here? Okay, then let's thank Gerardo again. So, thank you for your talk.
Thank you for the invitation.
Okay, so, and we are closing now the session. I think, Rene, you can stop recording.
Okay.